At the end of the topic, you will be able to explain the production of sound, discuss the propagation of sound through solids, liquids, and gases, understand that sound cannot travel through vacuum.
It is impossible to imagine a world without sound. The pleasing chirping sound of birds wakes us up every morning. Sound fills our days with excitement, emotions, and meaning when people talk to us, when we listen to music, or when we hear interesting programs on the radio and watch TV. Do you know how sound is produced? Sound is produced due to vibrating objects, such as hitting a tuning fork against a rubber block, plucking a stretched string, and striking a bell by a stone. These vibrations transfer energy through air and reach our ear. Sound can travel through solids, liquids, and gases. Sound needs a definite medium to travel. Sound cannot travel through vacuum. Click each image to hear a different sound. Every day, every moment, we hear something from our surrounding. This sound is due to the vibration of bodies. Sound travels faster in solids than liquids and gases. Take a metal scale. Hold it by your tooth. Now, hit the scale with a pencil. Can you hear the banging sound? From this simple performance, you can understand that sound can travel in solids, and it proves that sound requires a medium to travel. Let us learn the transmission of sound in detail. Now, we are going to learn about the transmission of sound in a medium such as air. We all know that sound is produced due to the vibration of objects. This vibration pushes the air molecule to vibrate. The air molecule transfers these vibrations to the next air molecule, and so on until it reaches our ear. The sound wave reaching our ear sets the eardrum to vibrate and passes through nerves to the brain. Thus, we hear the sound from the source. Sound can also travel through liquids. Click the animation button to understand the propagation of sound in water. Do you know about vacuum? Vacuum is an empty space which has no air molecules that can vibrate and carry sound waves. So, sound cannot travel through vacuum. See the animation to understand the propagation of sound in medium.
In this topic, you have learned sound is a form of energy produced due to vibration of objects. When sound waves enter the ear of the listener, it sets the tympanic membrane in the ear vibrating, causing the sensation of sound in our ears. Sound can travel through solids, liquids, and gases. An empty space which has nothing in it is called vacuum, and sound cannot travel through vacuum. At the end of the topic, you will be able to explain mechanical waves, differentiate transverse and longitudinal waves, define the terms associated with wave motion, deduce an equation for velocity of the wave.
Throw a stone in the pond and observe what happens. The stone pushes water particles in all directions, which in turn push adjacent particles, creating a pulse. When the stone goes down, the water particles again move to that point, and due to natural collisions, they produce another pulse. Each particle performs the same vibration performed by the previous particle. A series of such pulses form waves. Click on the animation to know the formation of wave. Some of the waves require a material medium to transmit through. Can you identify the waves that require material medium for their transmission? Yes, water waves require water medium. Earthquake waves travel by land, and also sound waves require air medium. These waves are called mechanical waves. Thus, in a mechanical wave, the particles move up and down and do not move along the wave. When we strike a bell gently with a stone, a gentle sound is produced. The sound which we hear travels from the bell to the ear through air medium. In the above example, there is no transport of particles of the medium, but energy is transmitted. You see different types of waves in your daily life, such as water waves, sound waves, X-rays, and so on. Can you differentiate between these waves? Based on the nature of medium, we have two types of waves. They are mechanical waves and electromagnetic waves. Mechanical waves always require a material medium to travel, while electromagnetic waves are even capable of traveling through vacuum. Water waves, earthquake waves, and sound waves are mechanical in nature, while X-rays, radio waves, and microwaves are electromagnetic waves. Now we are going to learn about transverse waves. Take a rope and attach a pen cap on the rope. Tie one end of the rope to a wall and hold the other end. Set it to oscillate up and down so that a bump is formed which travels forward. Now watch the pen cap carefully and record your observation. The pen cap moves up, crest, and down, trough, and the wave moves forward. The particles, pen cap, in the rope vibrates right angle to the motion of the wave. These waves are called as transverse waves. Light waves and water waves are the examples of transverse waves. View the animation on transverse waves. Now, let us learn about longitudinal waves. Take a spring and fix it perfectly horizontal. Now, push the spring forward, which produces a compression pulse down the spring. If we push the spring continuously, a number of compression pulses travel down the spring, and between the compressions, the spring seems to be freely moving, called as rarefaction. The spring oscillates back and forth with a continuous train of compression and rarefactions. Since the oscillating spring particles displaced along the direction of propagation of the wave, this wave is called as longitudinal wave. Sound waves are the best example of longitudinal waves. View the animation on longitudinal waves. Now let us learn about the wavelength of the wave. Wavelength is the length of one complete wave. When the particle of the medium vibrates about their mean position, they produce crests and troughs. The distance between two successive crests or troughs is called wavelength. Its unit is meter. We have learnt about crest, trough, and wavelength. Next, we will learn about time period. Time period is the time taken by the wave to complete one full vibration. Time period is denoted by the letter T. Its unit is second. Next important term associated with wave is frequency. Frequency is the number of vibrations or oscillations made by the wave in 1 second. Frequency is the inverse of the time period. Its unit is hertz. Knowing the frequency and time period, let us now learn about the amplitude of the wave. It is the maximum displacement of the particles of the medium from the mean position. Amplitude is the height of the wave from the equilibrium position. We have learnt the properties of a wave such as wavelength, time period, frequency, and amplitude. Now, we are going to learn about the speed of the wave. It is the distance travelled by the wave in 1 second. Speed is equal to distance divided by time. Unit of speed is expressed in meter per second. The relation between frequency and the speed of the wave is given as speed is equal to frequency into wavelength.
Reflection of sound. At the end of the topic, you will be able to describe reflection of sound, discuss reverberation of sound, identify the materials that can be used to reduce reverberation. If you shout in front of a hill, the sound will get reflected and come back in a few seconds. You can hear the reflected sound clearly. This reflected sound heard clearly is an echo. You can hear the echo in deep wells, tall buildings, and at hills. In ancient days, people constructed whispering gallery to hear the voice of persons clearly. It has a dome-like ceiling. Here, a single sound pulse will be reflected a number of times. The series of reflected sounds can be heard in the other part of the gallery clearly. Now, we will see how sound waves are reflected. Place a clock at one end of the table. Take two thick wooden sheets. Keep them perpendicular to each other without space between them at the center of the table. You cannot hear the ticking sound of the clock on the other side of the table. Now keep some space between the wooden sheets. Thus, one wooden sheet will act as a reflector and the other will act as a screen. You just listen from the other side of the wooden screen. You can hear the ticking sound of the clock. The sound waves are reflected from the wooden plate. Now see the animation to understand clearly. From the animation, we understand that the sound wave obeys the law of reflection. That is, the angle of incidence is equal to the angle of reflection. Now we will discuss how echoes are produced. If the reflected sound reaches the ear at least after 1/10 of a second, we can hear the echo clearly. If the time gap between the direct and the reflected sound is lesser than 1/10 of a second, we cannot hear the echo. So, in order to hear the echo, one should stand at a certain distance. We know the sound wave travels with a velocity of 340 meters per second. So the distance traveled by the sound wave from the source to the reflector and the reflector to the person in 1/10 of a second is equal to the velocity of sound into time. That is, 340 into 1/10 is equal to 34 meters. Therefore, to hear the direct sound and the reflected sound distinctly, a person should stand at 17 meters or more from the reflecting surface. Hard surfaces such as metal sheets, walls, plywoods are good reflecting surfaces.
Reflections of sound may be undesirable in some instances. The time interval between the successive arrival of the same sound signal gradually decreases with time. Similarly, the intensity of the sound signal also decreases with time. However, for example, the repeated reflections of sound waves from the walls of an auditorium interfere and build up to produce a continuous sound. This will result in a jumbling and continuous or persistent sound called reverberation. Some public halls or auditoriums are deemed acoustically poor because of reverberation. The roof and walls of auditoriums are generally covered with sound-absorbing materials like compressed fiberboards, rough plaster, or draperies or curtains to reduce reverberation. The material used for the seats also must be a good absorber of sound waves.
In this topic, you have learned echo is the repetition of sound due to reflection of original sound from any surface. The sensation of sound persists in our brain for about 1/10 of a second. The repeated reflections of sound waves from the walls of an auditorium interfere and build up to produce a jumbling and continuous or persistent sound called reverberation. Roof and walls of auditoriums are generally covered with sound-absorbing materials like compressed fiberboards, rough plaster, or draperies to reduce reverberation. At the end of the topic, you will be able to specify the audible range of sound, distinguish between ultrasound and infrasound.
We have learnt about the transmission of sound in air. We can hear sound from different sources. Each sound is different due to its frequency. We can hear sound with the frequency ranging from 20 Hz and 20,000 Hz. This is the human audible range. If the frequency of the sound is more than the audible range, it is called ultrasound. This high-frequency sound cannot be heard by human beings. A bat produces ultrasound. We have learnt about transmission of sound and ultrasound. Now we are going to learn about infrasound. If the frequency of the sound is less than the audible range, that is 20 Hz, it is called infrasound. Some animals like elephants and whales produce infrasound which cannot be heard by human beings.
There are certain animals which can produce and detect ultrasonic and infrasonic frequencies. Let us see the audible range of sound for certain animals. Click on the image for the audible range. 16 to 12,000 Hz, 100 to 32,000 Hz, 40 to 46,000 Hz, 16 to 40,000 Hz. Let us see the audible range of sound for animals like rabbit, bat, dolphin, and seal. Click on the image for the audible range. 1000 to 1 lakh Hz, 70 to 1,50,000 Hz, 900 to 2 lakh Hz, 1000 to 1,50,000 Hz. In this topic, you have learnt the audible range of frequency for human beings is between 20 to 20,000 Hz. Sound of frequencies above 20,000 Hz are termed as ultrasound. Sound of frequencies below 20 Hz are termed as infrasound.
At the end of the topic, you will be able to explain the mechanism of sonar, identify the uses of ultrasonography, define Doppler effect and Doppler processing, list down the uses of Doppler effect in sound.
SONAR is an acronym for Sound Navigation and Ranging. It consists of a transmitter and a detector that is installed in a ship or a boat. It measures the distance, direction, and speed of underwater objects using ultrasonic waves. This technique is used to determine the depth of the sea. It is useful to locate structures and objects, including underwater hills, valleys, submarines, icebergs, and sunken ships. The transmitter of the sonar produces and transmits ultrasonic waves. These waves travel through water. They get reflected after striking the object on the seabed. The reflected waves are sensed by the detector. The detector converts the ultrasonic waves into electrical signals which are appropriately interpreted. The time interval between transmission and reception of the ultrasound is recorded. The distance of the object that reflected the sound wave can be calculated by knowing the speed of sound in water and considering the above time interval. For example, the speed of sound in water is approximately 1440 meters per second. Let us assume the time interval to be 3 seconds. The distance of the object will then be 1440 into 3 by 2 equals 2116 meters. Click Animation button to know more about sonar mechanism. Ultrasound waves play a vital role in the medical field. Ultrasonography is an ultrasound-based imaging technique used to visualize the inner organs of the human body. In this technique, pulses of ultrasonic waves are passed through parts of the body which get reflected by organs. When several pulses are sent and received, it is possible to build a picture of the object reflecting the wave pulses. Ultrasound sensor is used to find the shape and movement of the baby during pregnancy.
We can observe the phenomena of Doppler effect whenever the source of sound waves moves with respect to an observer. We are most familiar with the sound of a train horn. Let us assume that the observer is standing on a railway station. As the train approaches the station, the observer can hear the sound of the train horn at a high pitch. Pitch is determined by the frequency. In the same way, when the train moves away from the station, the sound is heard at a low pitch. This apparent change in frequency due to the relative motion between the source and the observer is called Doppler effect. If we can measure the change in the frequency of the transmitted pulse and the reflected pulse, the velocity of the object reflecting the pulse can easily be calculated. This is called Doppler processing. Doppler effect find useful in the following ways. Click the titles to know about the uses of Doppler effect. SONAR. Doppler processing is used in sonar to find the velocity of the object reflecting the transmitted pulse. Bats. Bats can send as well as receive ultrasonic waves reflected by the prey and obstacles. It can navigate and locate their prey by the Doppler shift in frequency. In airports, Doppler shift can be used to identify the difference between the echoes received from the moving aircraft and the echoes received from stationary objects. The accurate determination of height, speed and distance of approaching aircrafts can also be done using Doppler shift. Traffic control vehicles. The speed of a vehicle can be accurately calculated using Doppler shift in frequency. In this topic, you have learned SONAR is an acronym for Sound Navigation and Ranging. This technique is used to determine the depth of the sea. It is useful to locate structures and objects including underwater hills, valleys, submarines, icebergs, and sunken ships. Ultrasonography is an ultrasound-based imaging technique used to visualize the inner organs of the human body.